All right, so I'm just going to run through chapter 8 ideas. Most of this lecture we already saw in class, but let's just jump into it. So chapter 8, it's about hypothesis testing, and hypotheses have tails. Okay, what do I mean? So for example, scores on a standardized test have a mean of 70. Some modifications are made, okay, and an educator believes that the mean may have changed. Okay, state the appropriate null and alternate hypothesis. Okay, so I suppose if I was to color code this a little bit better, then what I would do is I would say the null hypothesis corresponds to the old data. So the null hypothesis, which we're going to denote with an H subscript 0, is that the mean has not changed. So there's some new mean, which we don't know, and we're saying it's equal to the old mean. Anytime we subscript with a 0, the way we tend to read that in the sciences would be like initial. So this would be, sorry, initial hypothesis. But then in stats, they end up calling it null. So this is the null hypothesis. This is the null mean. Um, but you could also think of initial hypothesis, initial mean, the data we had going into it, right? Our alternative hypothesis, we're going to subscript with a 1. And in this case, we're just curious if things have changed. So we don't know if the new mean is higher or lower. We just think the new mean might be different from the old mean. Okay? So that's all that's going on. This type of guess or hypothesis is called a two-tailed hypothesis because the idea is, let me draw a little curve. Um, there's some old mean, which I guess if I was to color code, let's say I make this blue, color blue, great. And so if that was still true, then our data, I don't want this, our data would lie on this bell curve where the mean is mu0. Okay, so we go out and we give this test to 100 students or something, and we take their average. And so the old mean, by the way, was 70. That's what this problem says, highlighted in pink right here. And we go out and we test a bunch of students, we take their average, and then maybe their average ends up being 75. Okay, is this enough evidence to say that the average has changed? That's the type of question we're going to be looking at, and maybe the blue curve is no longer the distribution, and now maybe it's this red curve, right? Maybe the distribution has shifted over time. We have a new distribution, we have a new mean. But I don't know, maybe. So there, the students got smarter, so to speak. They started scoring better, right? They started scoring better. Maybe actually our X bar was down here. Maybe it's 60, right? Maybe we should actually have this curve. Whatever. Okay, it's a little bit off, whatever. Um, the we don't know whether to shift left or right. We don't know whether we should be in this tail or this tail of the blue original distribution. Okay. And so there's going to be some zone where if we're far enough away from 70 in this zone, or if we're far enough below, maybe in this zone, where we'd say, okay, we're far enough away, there's good enough evidence to think we've changed in one direction or the other. Okay, there's two different ways we go. It's two-tailed. Okay, the mean monthly rent for an apartment in a certain city was $800. And then people go out and they collect some data and they believe the mean rent is higher this year. So, all right, the null hypothesis is that the mean rent is 800. Okay. Oh, I put down mu0 here, but they gave us a value of mu0. Sorry, and here I said it more explicitly. Mu0, the way we use it, and it's going to show up in your calculator sometimes, is this is the notation for the known value of the old stuff, right? So 70 is my mu0. In this case, 800 is my mu0. And we're saying is the new mean, is the new mean equal to the old mean, right? That's what the null hypothesis is going to be. The new mean is equal to 800. 800 is my mu sub 0, my mu naught. The alternate hypothesis, is that mu is bigger than 800. We think rent prices have gone up, right? So since things are bigger, if you have a number line, here's 800, and we're saying maybe mu is over here. This is right-tailed. And then we're going to have an example of a left-tailed hypothesis. So Some cereal boxes are being filled on an assembly line at 20 ounces, and an inspector thinks the mean weight may be less. So the null hypothesis is that the equipment works just fine. It fills to an average of 20 ounces. The alternative hypothesis is that there's something wrong with the equipment. It's underfilling these cereal boxes. Okay. And this is called left-tailed. Okay. So technically speaking, these the reason we want to specify, okay, is because it narrows our focus on how we want to compute the probability that our data value is extreme as it is. And so I want to make more sense of this with examples. Here I have two different snippets, one from the textbook, which is the 8.2 one, and one from ALEKS. And the 8.2 section is very unrealistic. It's not what we're really going to be seeing in this class. So I want to spend more time doing the 8.3 section, and I also want to highlight the difference, right? So first, let's look at the similarities. So what's going on? So AAA, the American Automobile Association, reported the mean gas price for a gallon of regular gasoline in the city of Los Angeles on November of 2023 was this. So, okay, we have an old mean price for a gallon of gas, right? A recently taken simple random sample. Okay, so a simple random sample of 50 gas stations in Los Angeles. So now we're going to go out and collect some data. And maybe I should use a little bit more of a darker orange to make it pop a bit better. Okay. Had an average. Okay, so the sample had an average of 4.98 per gallon. And then there's this lingering weird thing. It says, assume the standard deviation of prices is 15 cents. And so when it says that, it's talking about for all gas in California, we somehow magically know how much prices vary, even though we don't know the true average for the gas price in California. Whereas, okay, if we look at this other statement, let's see. So what are we looking at here? The NHS reports describe a study in which a sample of 345 one-year-old boys were weighed. Okay, so we have a sample. Their mean weight was this many pounds with a standard deviation this many pounds. So now this standard deviation is describing the sample, not the population. Here, this is the population, not the sample, right? So do you see how in 8.2, this average of 4.98 for the sample, for the simple random sample, this simple random sample, we have the data for its average, but the standard deviation data we have is not for the sample, it's for all of gas prices throughout California. Whereas in 8.3, the standard deviation we have is for the sample. And that's much more realistic, okay? This is the kind of stuff we're going to see over and over and over. Now, if we were to go through and finish this, they again get really similar because we're going to be doing hypothesis tests and stuff. And so someone's going to come along. So in the gas price one, an economist comes along and they want to determine whether the mean price for gas has gone down, right? Whether it's less than that. Whereas in the weights of one-year-old boys, a pediatrician comes along, claims the mean weight is greater than 25, right? Again, okay, maybe I should actually, let's see if I can rearrange this. Yeah. Okay, we'll put this over here. Oh, whatever, who cares? Pediatrician claims the mean weight is greater than 25. So, okay, and I think I actually still have this up in ALEKS. Maybe I do, maybe I don't. Nope, that's a different problem. So let's take a peek at this. And let's just run through how to do this type of problem. So this is chapter 8, part 2, content. I don't actually remember which one it is, so I'm just going to pick one. We'll see if this is, yep, this is baby weights. Okay, great. So in this context, now I have 330 one-year-old boys, so that's the sample, and we weigh them, and their mean weight is 25.4 pounds with a standard deviation of 5.3 pounds. Fine. Pediatrician claims the mean weight for one-year-old boys is greater than 25 pounds. So the null hypothesis is that they're wrong. It's that mu is equal to 25. The alternative hypothesis is that they're right, and they are claiming the mean weight is greater. So they are claiming that mu is greater than 25, okay? This hypothesis test is a right-tailed test. Okay, so let's go ahead and check that, and everything should work out. Great. Compute the value of a test statistic, rounding us to 2 decimal places. Okay, so what the heck is going on with this? So, what are the numbers we need to remember? 25.4 is the mean, 5.3 is the standard deviation, and the sample size is 330. So let's go to a calculator. Stat, we're always going to be looking at this test menu now, and everything that's a hypothesis test will have the word test in its name. So z-tests, that turns out to be section 8.2, which we don't really touch much. T-test, that's 8.3. We're going to use that all the time. It's also 9.2. We're going to see t-test multiple times in this class. So that's the one we want to go with. Enter. And we're going to feed the calculator some statistics. And it says, okay, what's the null hypothesis here? So that's what we filled out. That was the, oops, sorry, there we go. It's the mu is equal to 25. And the calculator calls that mu naught and saying, what do you think the initial, what's the old mean? So 25. Okay, what's the sample that you got? What was its average? Well, that's 25.4. 25.4. Oops. So annoying how many times I have to click into the calculator versus into the window. And I think this was 5.3 and 330. Let's just check. So I know the 330 is right. And yes, 5.3 is the standard deviation. And okay, what's the null hypothesis? Or not null, sorry, the alternative hypothesis. Well, this pediatrician thinks that the children are greater. They're gaining weight, right? So the true mean, mu, which is on the very left-hand side, how do we want to compare it? Do we want to say it's not equal to mu naught? Do we want to say it's less than mu naught or greater than mu naught? And the answer is greater. We want to say it's greater. Okay. So then we can go ahead and calculate. And we find that with the values, okay. Let's make sense of this. So there's this thing called a test statistic, which is this t value of 1.37, and there's a probability, which is the p-value 0.0856. Okay, so let's hop back here and notice it wants the test statistic, right? So that was the 1.371, and let's see how many 2 decimal places. Okay, 1.37. And I'll draw a picture and make sense of this in just a moment. For now, I'll just show you, here's how we're going to answer it all. This says round to 4 decimal places. So let's go back here. The p-value 0.0856, and that 6 would round up to a 7 because there's another 5. 0.0857. 0.0857. Check. Great. All right, do we reject? So here's the deal. If the true mean for 1-year-old boys is 25 pounds, so if that's the case, then the chance of going out and collecting a sample of 331-year-old boys and having their mean be 25.4, well, actually, okay, I should draw a picture at this point. Okay, so we're sort of here. Let's see if I can scale this down a bit. So here's what's going on. So let's get a line. Okay, we'll get a little curve. Okay, and the mean is 25. Now we go out and we sample and we're here. X bar is 25.4. Now, because the null hypothesis, H1, is right-tailed, the whole point of this is how do we quantify how rare this type of finding is? And the way we do that in stats is we say, well, look, actually the probability of getting exactly 25.4 is 0. This happens with distributions for continuous things. The probability of it landing on exactly one specific value is 0. And you need sort of a range to be able to get probabilities. And so being right-tailed, we say, well, tell you what, how about we just compute the probability of getting what we got or something more extreme. So this p-value of 0.0857 that is the probability, one day I'll be able to spell probability of getting X bar greater or equal to 25.4. So it could be equal to 25.4. It could be as extreme as we got, or it could have been more extreme. Maybe they weighed 30 pounds or something like that, right? So if, I should say, this p-value is the probability of getting that, assuming that the null hypothesis is true, right? So if the average 1-year-old weight for boys, boys at 1 year old, whatever, if their average weight was 25 pounds, then the probability of this sample of 330 boys having a mean of 25.4 or higher is about 8.5%. It's 0.0857. Okay. Now, the fact that I shaded and computed all this for my area, that's because it's right-tailed. If it was left-tailed, then we would have actually found all this area. And if it was two-tailed, well, now this figure is getting really confusing. You would make a symmetric cut. So this is 0.4 above 25. We'd go 0.4 below 25, which is, I guess I do want this, 24.6 would be that spot. And we look at how probable is it that we're just this far away from the mean? And we look in both directions. Okay. So anyway, that p-value is giving us a probability where you sort of shade according to what we're looking at. All right, do we reject the null hypothesis? So no, we do not reject, and let's make sense of that. I'll go ahead and hit check real quick, and it can get a little green check. So there's going to be some threshold, and that's the alpha value. And if we look at this problem, it says alpha equals 0.05, which is really common. And what that means is if the probability of getting what you get or something more extreme, if that p-value, if p is less than alpha, which we can see is not true, right? 0.08 is bigger than 0.05, so this is not true. But if it was true, and in fact less or equal, so if p was exactly 0.05, then we're going to reject H naught. So, if this average sample size, not sample size, if this average mean, that's redundant. If for this sample of 331-year-old boys, if we got an average weight of like 26 pounds, that would be enough to reject, okay? Anything where the p-value is less than or equal to 0.05, and I bet that would happen at 26 pounds. So anyway, we do not reject, state the conclusion, there is not enough evidence to conclude the mean weight of 1-year-old boys is greater than 25 pounds, right? There's not enough evidence to reject, okay? Look, it's not likely that this is the average we would get, right? An 8% chance is not very high. So this, even though it might seem like to us that 25.4 is pretty close to 25, that's actually pretty rare, essentially because a standard deviation in this case, so we have a standard deviation of 5.3, but then you have to divide that by the square root of the sample size, which was 330, and that's going to make this thing really small. The square root of 100 is 10. This is 10 times 3, so that's going to be like 17. So this is going to be about like a 0.3. Okay, so we're about 1 1/3 standard deviations away, right? So this is not drawn to scale, but one standard deviation would be about 0.3, and we're at a 0.4. So 0.4 is about 1.3 times 0.3. Okay, so we're about this many standard deviations away, and that's what the test statistic is actually telling us. This thing up here, the t value, when it says t equals 1.37, this was me just doing off-the-cuff mathematics to try and estimate the standard deviation. But in fact, we are 1.37 standard deviations away from the mean. So whatever, we're not going to use the test statistic very much, but it's good to know once you're 2 standard deviations away, you tend to be pretty rare. You're looking at about, you're probably going to reject the null hypothesis. You're going to cross that threshold. Once you're 3 standard deviations away, you're very rare. Anyway, okay, so that's that kind of problem. And where are we? Right. So I was just beginning this lecture, and we're starting to see a lot of new vocab pop up. We got null hypothesis, alternate hypothesis, left-tailed, right-tailed. So here's the thing. Section 8.1 in the textbook, and in fact, let me just pull up your ALEKS homework, where it's chapter 8, part 1. And you'll see it's mostly going to be labeled as conceptual problems. There's a lot of terminology. That's mostly what 8.1 is. But I think terminology is pretty hard to learn without example problems, right? So notice your first exercise, conceptual, second, conceptual, third, conceptual, 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 right? It's not until exercise 5 where you start to get some non-conceptual, and then conceptual shows back up again. So anyway, let's take a quick peek at what this first exercise is, and that should pop up over here now. Okay, so the null hypothesis states that a parameter is equal to a certain value, whereas the alternate hypothesis says that we differ. Okay, so that's just some stuff that you could have picked up. That's fine. Let's see what happens once we get to problem 5. Oops, wrong one. All right, determine if we're left-tailed, right-tailed, or two-tailed. So since mu lies to the left of 18, sorry, I don't know that it lies to the left. I look at the alternate hypothesis, the H1. Mu lies to the left, that would be called left-tailed. Okay, that's how we would compute these p-values, where we start to shade to the left, right? So that's what's going on with that. I don't know if these are really worth it, but now this, I think, is where we start to get to p versus alpha values, which we just kind of talked about. Okay, error typing. So maybe we'll just hop into this. All right, the point is, chapter 8, part 1, lots of conceptual, lots of terminology. We'll do some error type problems. That's going to show up too. That's pretty conceptual stuff. 8.2, we basically don't touch in this class. It would work basically the exact same as what I just gave in the example. The only difference is when we go to the test menu, you would do the z-test. But again, don't expect that. I don't even think that shows up on the exam or on your homework. T-test is what we're going to use a lot more. And in fact, our goal is to make sense of pretty much all the other tests on here. Okay. Okay. So hypothesis testing for an unknown population standard deviation, that's going to follow a t-distribution. But maybe a different way that you could think of this is you have a sample with a mean and a standard deviation. And then you're going to go, oh, okay. When the problem gives me a sample with a mean and standard deviation, I'm thinking t-distribution, okay? The standard deviation here is for that sample, right? In the Wayne, the 1-year-old boys, their standard deviation was 5.3 pounds for just that sample. If we use sigma, we're talking about the population. Okay, and then 8.4, hypothesis testing for proportions. Okay, let's get into error types, and then we'll just do a few more examples and call it good. So error types. So here's the thing. We don't know what the true mean is, okay? So H naught says that the mean is equal to some value, which we call mu sub 0, okay? That might be true, but when we run our tests and collect some data and maybe X bar is pretty far away, the evidence might make us reject thinking that H naught is true. So let's look at, I'll just combine this with these examples here. So a dean of a business school wants to determine whether the mean starting salary of graduates is greater than $50,000. So the null hypothesis is that it's equal to 50,000. The alternative is that they're making more than that. Okay, suppose the true mean is 50,000. So we're going to assume H naught is true. We're in this setting, okay? And the dean rejects H naught. That's what's called a type 1 error. We've rejected H naught. When H naught was true, we made a mistake. That's a type 1 error, okay? Now, if the true mean was 55,000, that means H naught is false. And if the dean rejects H naught, that's the correct decision. Okay, that's making a correct decision. It was false, we reject it. Alternatively, the true mean could be 55,000, but when you poll your graduating class and ask them what their starting salaries are, only the people making less money on average tend to respond. And it looks like they're not making as much as they actually are. So you don't reject. You're thinking, no, it looks like it's 50 when you should have rejected, and that's called a type 2 error. Type 2 error. So these types of questions, they're going to show up on your homework. They're going to show up on your exam. Knowing the error types is definitely something we want you to take away from this class. For me, I often have to redraw this table because there's nothing in the name type 1 error that makes me think, oh, H naught is true and I reject H naught. But okay, how else can we think of type 1, type 2 error and all that stuff? So what should you be? Probably supposed to be blue. So innocent until proven guilty means the null hypothesis is innocent. Okay. So if you get away with a crime, that means you were not innocent. So you were guilty. Okay. You're not innocent. H naught is false. But if you get away with the crime, that means the jury thinks you're innocent. So they do not reject the idea that you're innocent. You get away with the crime. Okay. Whereas if you're wrongfully convicted, that means you are innocent. You actually are, but the jury don't know that. And the prosecutor convinces them to think you're guilty. So they reject your innocence, even though you are. That is a type 1 error. Okay. So type 1 is a wrongful conviction, and type 2 is getting away with a crime. Okay. Don't know if that will help, but that's another way we can think about this. All right, that absolutely shows up on your homework. Let's take a peek at that really quick. And actually, oh, I should have labeled questions where it shows up. 3, 4, 14. Sure, why not? So this is all still in part 1. Let's see what question 3 is. That should pop up on a new tab. Oh, I see. Okay. So alpha is the probability of a type 1 error. So yeah, I'll say that. We're about to look at that. I'll draw pictures, fine. So there's that. 3, 4, let's just look at 14. I think 14 is going to be the stuff that I want us to see. If it loads, let's try deleting that, coming back to it. 14. There we go. Kai will perform a hypothesis test at the 0.01 level. Brendan will perform the same test at the 0.05 level. Brendan. If H naught is true, who has the greater probability of making a type 1 error? So look, alpha is essentially the probability where if H naught is true, you're going to reject H naught. Alpha is the probability of a type 1 error. So Brenna has the greater type 1 error probability. Okay. All right. Whatever. Let's look at those with maybe this next kind of slide. Yeah, all those questions seem to look at, oh, 8 through 10. That was supposed to be 8 through 10. It looks at the wrong spot. Let's do that. Let's do 8 through 10. All right, 8. There we go. Determine whether the outcome is type 1, type 2, or correct decision. So test is made where mu equals 55 is the null, mu less than 55 is the alternate. The true value mu is 55. H naught is true, and yet H naught is rejected. That's a type 1 error. Okay, when in doubt, you can consult that table, but that's a type 1 error. So questions 8, 9, and 10 are that kind of question. All right. The probability of a type 1 error, so I should really make this say type 1 error, of type 1 error is equal to the alpha level. Okay, I originally had a different title, but it's equal to the alpha level. All right, so why is that? So, all right, if H naught is true, then the thing we're looking at is described with this red distribution curve, right? That's what happens if H naught is true. Now, in order to draw a picture of this, I need to give an alternate hypothesis. So I'm going to draw a right-tailed example. If it was left-tailed, then you just move the blue bump to the left. And if it was two-tailed, you sort of have two different blue bumps that you're looking at. But let's just focus on right-tailed. So look, if you go out and your data has an X bar that's right there, the evidence does not say that we should shift to the right. The evidence does not say that X bar is likely coming from this blue curve, okay? Here's the thing. So as X bar drifts more and more this way, like what happens if X bar is here, right? And now you can sort of say, well, look, the probability of being under the red curve is way less than the probability of being under the blue curve, right? You're starting to get more evidence for blue than there is for red. So an X bar out here, it's more likely you would reject H naught. You'd say it's likely not modeled by the red curve. And so the question is like, where's the threshold? How far do we drift this way until we reject? And that's determined by alpha. So alpha is an area. And how do I want to do this? Maybe I'll draw it right here. Okay. So there's some area, alpha, and you can imagine that area is 0.05. And that area is shaded right because this is a right-tailed example. Okay. And in order to get that area, there's some spot known as a critical value. So I'll put this down as, I'll say T sub alpha, where if our X bar moves to the right of that spot, we're in the rejection zone. We're going to reject H naught, right? If X bar moves to the right, the probability of X bar or something more extreme is less than alpha, okay? In other words, this area to the right of X bar is less than all the green area that was to the right of T alpha, okay? So anyway, what's the probability we land in the rejection zone? Well, it's the area of the rejection zone. It's alpha. That's why alpha is the probability of a type 1 error, because it is the probability of rejecting H naught, even though H naught is true. It's this area under the red curve. Being under the red curve means you're saying H naught is true. And then rejecting it says, all right, you're way off to the side here. What's a type 2 error? A type 2 error is when H naught is false. So now we should look at the blue curve. But yet we don't reject H naught. So that's the kind of thing where like, what if X bar, this is getting kind of busy now, so let me clean this up a little bit. What if X bar was over here, right? I'm not in the rejection zone, so I'm not going to reject H naught. It's not likely that the blue curve models what was happening, but it turns out it did. It turns out because I'm imagining a type 2 error. A type 2 error is when you should have rejected that. This should be what's happening. And yet, when we run our tests, the data suggests we should stick with the red curve. The red curve is more likely to explain our outcome. Okay. So anyway, alpha is the probability of a type 1 error, and alpha is proportional to the type 1 error, and it's inversely proportional to the type 2 error. Okay, whatever. You can play around with those error questions on ALEKS and see how it's going. All right, so this was all from a thing I did in class where I like labels the spots A, B, like maybe this is B and stuff like that. Not too worried about it. Here's the main takeaway. If H naught is true, then alpha is the probability of a test statistic being extreme enough to reject H naught, i.e. a type 1 error. Okay. All right, let's do another hypothesis test. I've been rambling for long enough. This question's from the textbook, but let's just do a homework question. All right. Your chapter 8 part 1, it's mostly all conceptual stuff. This looks like it's an actual exercise. Let's see. Yeah, I don't want to deal with that, but there were questions on that one in class, so we'll see. Let's go look at the part 2. Part 2 of chapter 8 has a lot of questions to do that are hypothesis tests. Content. And you see they're pretty much all 8.3, right? Let's take a look at this one. In fact, I think this is the newborn. Yeah, it is. So let's look at the next one. There we go. Okay, cool. So sometimes you have to put it in a calculator, uh, which, man, I really don't want to do, but we'll do it, I guess. That's 20, 26. All right, fine. So stats, enter. I need to clear this. Enter. And I need to clear this. Enter. And I have to enter all this data. So let me take a quick photo. I can just do it. Boom, boom. All right. We have got 20, 26, 5.1, 21.3, 18.2, 9.9, 14.9, 18.4, 34.9, 31, 9.8, 33, 21.3. Nope. Damn. There we go. And 16.7. All right, cool. So I've got all that data in there, and let's finally read the problem. So in a study determined whether counseling could help people lose weight, a sample of people experience a group behavioral intervention, fine. Involve weekly meetings, fine. The following data are numbers of pounds lost for 14 people. Assume the population is approximately normal. So because our sample size is only 14 and we want it to be at least 30, that type of setting is when the question will pretty much always say, and the population is approximately normal, or the population is normal, or something like that. Perform a hypothesis test to determine whether the mean weight loss is less than 15 pounds. Okay, so the null is that it's not less than 15 pounds. And the closest you can be without going over it is 15. Okay. The alternative hypothesis, where the mean weight loss is less than 15 pounds. Well, I guess it's that mu is less than 15 pounds. That's what we want to know. This would be a left-tailed test because mu moves to the left. Let's take a peek. Sweet, there we go. Now we need test statistics and all that. So now this is when we go back to the calculator. All their values are in L1. Go back to the test menu. This is a t-test. But this time, we're not entering statistics, we're entering data. And the null hypothesis is that the mean weight loss is 15 pounds. So I should make this a 15. We're using list one. Don't worry about frequency. We don't touch that. The alternative hypothesis is that they lost less than 15 pounds. So now let's go ahead and calculate. Our test statistic is this 2.1249, blah, blah, blah. I'll say 2.125. That means they are 2.125 standard deviations away from 15 pounds, okay? Away from the mean. So where are we at? 2.3 decimal places, perfect. 2.125, check. What's the p-value? So we have to go back to the calculator. It's just under our test statistic. It's 0.9733. Okay, and that says 4 decimal places, 0.9733, check. Great. Do we reject? So, all right, we're supposed to use an alpha level of 0.01. So is p less than 0.01 or is it bigger than 0.01? It's bigger, so we do not reject. We fail to reject. We do not reject. Check that. And there's not enough evidence to reject, so there's not enough evidence to state that the mean weight loss is less than 15 pounds. Okay. All right. Good, good. So, what's critical value? Critical value, in this rambling bit, it was that T sub alpha. We're not going to really have to use critical value. It might show up from time to time, but that's not a key thing here. What I want you to know is that if the probability of what we get slash something more extreme is less than alpha, then we reject H naught, okay? But there's another way you could state this condition because line, okay, and then a curve, boom. So alpha is some area, and that area begins somewhere, and the name of where that begins is the critical value. And so if you go and you do a test, so like we just looked at weight loss, right? And their average weight loss was some amount, okay? If that average lies in this window, you would reject. And if that average lies in the window, that means that P is less than alpha, like that's the only way it can happen. But you could state that using what's called a critical value, and you could say that, okay, if X bar is further from mu naught, right? So here's mu naught. If X bar is further from mu naught than, I'll just say Z alpha, sometimes it's called T alpha, but it's the critical value, then you would reject. But we don't really use that method, okay? Point is the critical value is where that alpha window begins, okay? All right, so there's a thing called a test statistic. The calculator computes it. We pretty much don't do this type of stuff. We're mainly gonna look at t-test and some other stuff. And in the calculator, it would be called little t, and we just saw that and filled that out on the last Alex page. And we're basically never going to use it aside from when things ask for it. But the way we do a hypothesis test is to get a p-value. Okay, so our test statistic is the thing that we know the distribution of. That's some deeper math, but you could think of it as X bar. But technically, like when I write an X bar here, I'm supposed to write T for test statistic. And it's not just X bar, it's sort of like a z-score, right? So we did X bar minus mu over a standard deviation kind of thing, or what's called standard error. And if P is less than alpha, we reject H naught. Alpha is our threshold. So alpha is a probability, it's an area. The critical value is where that area begins, the so-called critical value. So this is just sort of a broad overview of what all has happened. All right, this is a type of question that doesn't require any computation, but it can test your conceptual knowledge and doesn't really show up on Alex. But okay, so suppose a hypothesis test is performed where the null hypothesis is that mu naught equals 2 and the alternate hypothesis is that mu is greater than 2. Okay, fine. So we do a test and we have this test statistic, 2.481. It means that what we get is about 2.5 standard deviations away from the mean. Its p-value is 0.0177. Okay, so it's not very likely. It happens about 2% of the time, or 1.7% of the time. Assuming H naught is true, was the probability of obtaining a result more extreme than the test statistic? And it turns out that's the p-value. The answer here is 0.0177. That's what a p-value is telling you. Remember when I drew that little thing? And you're going to say, Anthony, all these drawings look the same. How am I supposed to know when you're... So look, we have this test statistic, which in this case was 2.481. And so that's 2.481, okay, equals that. And the p-value is all this area over here. This is the stuff that's more extreme, okay? So the probability of being more extreme than the test statistic, that's actually what the p-value is telling you. It's the probability of something more extreme happening. So that's the answer there. Okay, if H naught was false, so that means we should reject this in order to make the correct decision. If H naught was false, what type of error occurred? So if we had that little table, there's the true false for H naught. And then there's we reject or we don't reject, no reject. And if you remember, this is type 1, this is type 2. So if H naught is false, we're in this column. I bet we made a type 2 error, and yes, we did, because our p-value is not small enough to reject, right? It's not smaller than alpha. So we did not reject H naught, and we should have. That's a type 2 error. So look, how can you play with this problem to make your own version where maybe a type 1 error occurs? Or, I don't know, see what you can tweak here. Maybe you change alpha. Maybe you change your test statistic and change your p-value. Something like this. See how you can tweak this problem to make it a type 1 error or a correct decision. Would you rephrase any of the part A where maybe the answer is not, so look, okay, what's the probability, as asked, this is what's the probability for a more extreme test statistic, and it's the p-value. What's the probability for a less extreme test statistic? That's 1 minus the p-value, right? So anyway, all right, now we get to 8.4, some proportion stuff, uh, which actually, let's just look at chapter 8, part 3. That's pretty much all proportion questions. So chapter 8, part 3. And we'll just jump in with a problem. All right. Marketing manager for a phone company claims the average percentage of kids age 8 to 12 who have phones differ from 51%. Okay. So they're claiming that a percentage differs. They're not saying it's bigger than it. They're not saying it's less than it. So the null hypothesis is that the proportion is exactly 51%. Okay. The alternative hypothesis is that it's not 51%. It differs from 51%. This is a two-tailed test. Okay. All right, compute the test statistics. So we need to put this in the calculator. We do a survey of 830 children. So I'm looking just below where it says kids with phones in bold, right? So there's in a survey with 830 children. 415 of them had phones. Okay, so let's go to the stat menu, go to the tests. We have one proportion and we're trying to do a test with it. We're trying to do a hypothesis test. So we find the thing in the calculator that says one prop in test. Okay, so we're gonna go with that one. All right, what are we assuming is what's the null hypothesis for the proportion? It's 0.51, 0.51. All right, now when we went out and collected and surveyed some kids, we surveyed 830 of them. That's our sample size. 415 of them had phones. So 415 is what the calculator calls X. What you need to know is that X divided by N is the sample proportion. So X is how many of the sample test positive for something or say yes to something, right? In this case, they have phones. They said yes to having phones. And N is just the sample proportion. And we want to know, are these two things like, does the data support 0.51% or sorry, 0.51 or not? And in this case, we would not reject. The test statistic is this letter Z here. And maybe you're noticing now in the test menu, when we've done a t-test, the test statistic was labeled with a T. When we did a one prop Z test, the test statistic is labeled with a Z. And in general, the name of the test statistic also appears in the name of the test. So the test statistic is negative 0.5763. Let's go over here. We want two decimal places. So negative point, and it was 576, which becomes 58. Great. What's the p-value? So we don't want p hat. We just want this p, which is 0.5644. So 0.5644. There we go. Do we reject? No, we do not. In fact, we were more than 50% likely to get what we got. We were 56.44% likely. There's not enough evidence. Okay, so that's that problem. Let's see what other stuff we have. That was problem 1. Let's take a peek at problem 4. A community survey, 1,923 people in Colorado, and asked how long it took them to commute to work each day. A sample mean. Oh, interesting. So let's get some scribbles going. Okay. If you have a sample mean and standard deviation, some kind of t-test, okay? Whereas if the word proportion shows up, proportion or percent, right? Or if you're looking at some number out of some number, right? Uh, that's going to be a proportion test. So, and so once I read the word mean for that mean commute time, I double checked the title. You all will just see this as problem number 4 on your chapter 8, part 3. But you can see that we see it's section 8.3 in the textbook. 8.3 was t-test. So this is actually a t-test problem. I want to do a couple more of the proportion problems. So I should do, let's look at number 5, I guess. Why not? That's going to be 8.4. All right. A poll taken by Software Usability surveyed 341 video gamers, and 113 of them said they prefer playing games on console rather than on computer or handheld device. An executive at the game console manufacturing company claims that more than 29% of gamers prefer consoles. So, P equals 0.29 is the null hypothesis, and they're claiming it should be higher. They're claiming more than 29% of gamers like consoles. So that's going to be a right-tailed test. Okay, cool. Let's check that. And then after that, we have to jump to the calculator, right? All this other stuff's going to be in the calculator. And so the numbers I have to remember, X is 113 and N is 341. So test, one prop Z test is option 5. This was the 29%. I don't remember now. Let's go take a look. 113 and 341. Okay, fine. 41. And they were claiming that it should be greater than 29%. Let's calculate. Okay, they got a test statistic of 1.68 and a p-value of 0.046. And so the value to beat and to be lower than is 0.01, so we're not going to reject in this case. The test statistic, what was that? 1.6839. Hopefully you get it by now, what you put in 1.683 would just be 8. P-value, yeah, I don't feel like doing this. Hopefully you get it. So one prop Z test is what we do here. That's good for today. So I'm just going to